before the break, we took a look at velocity time graphs, the shapes of velocity time graphs, and what they meant, and also some calculations and readings off of those velocity time graphs to determine displacement, velocity, acceleration, and so on. Let's real quickly go through the shapes here first. Let's make sure that we're on target with those, and then we'll go through the calculations that we did before the break here. Tell me what the first one means. Velocity time graph, straight line. Yep. No, it's not a constant velocity. Okay, be careful. If that was a position time graph, that would be constant velocity. But velocity time graph, you can see the velocity is changing, right? It's getting bigger. Rosie? Yeah, that's a uniform acceleration. You could say constant acceleration as well. Okay, that's the acceleration that we usually deal with, uniform acceleration. What about the second one? What about the second one? Constant velocity. This one is, if it was a position time graph, it would be stopped, right? But it's a constant velocity here because you can see the velocity is not changing. What about this one? Good. It's a decreasing velocity. Let's call it a constant negative acceleration, but decreasing velocity works there. What about this one? Yep. Yeah, the acceleration is, not only is the velocity increasing, but the acceleration is increasing. So the rate at which the velocity increases. And the last one, the rate at which the velocity increases. The velocity is increasing here, right? It's getting bigger and bigger and bigger. But the rate at which the velocity increases decreases. In other words, this is still an acceleration, a positive acceleration, but a decreasing acceleration. It's like putting your foot on the gas pedal right on the floor and then easing off. You're accelerating really quickly in the beginning. You're still accelerating 5 seconds later, but you're not accelerating as quickly because you've eased off the gas pedal. Still speeding up, just not as quickly as you were. All right. We said that we can find a number of different things from these velocity versus time graphs. The first thing was finding the velocity at a certain time. We just went up and over. Up and over here, the velocity would be 15 meters per second. The change in velocity is final minus initial. So it's going to be up and over, subtracted 2. This is going to be about 33 minus 3, which gives me about 30 meters per second. The acceleration of the object over the entire graph is going to be the change in velocity over the change in time. 30 meters per second divided by 10 seconds. And the displacement, ooh, this was the tricky one, the displacement. How do we find that? Yep. Yeah, the displacement is the area. Now the area is tricky here because we've got kind of a weird shape, right? It's kind of a triangle, but kind of a rectangle. What do we do there? Let's break it up into a triangle and a rectangle. Call this A1, call this A2. Area 1 being a triangle would be found by 1/2 base times height. In area 2 being a rectangle would just simply be base times height or length times width. Good? All right, we had 4 questions. I'm going to put up the answers to those 4 questions, and then we can go over one or more of those questions if we need to. From your worksheet, question 2, question 3, and question 4. Let's take a look at question number 3 then. Velocity time graph. We want to find the velocity at 12 seconds. So what are we going to do for finding the velocity at 12 seconds? Whenever we want to find something that appears on the y-axis, we're going to go up and over. So let's go 12 seconds, up, over, gives me 5 meters per second. The acceleration between 0 and 8 seconds. Remember, to find the acceleration, we want to say A is equal to delta V divided by delta T. But we need what delta V is. Delta V between 0 and 8 seconds is, well, V final is 5. V initial is 0. 5 minus 0 over 8 seconds, which gives me 0.625. Yes? What's acceleration between 8 and 18? Well, this is an easy one. Don't even do a calculation for this. Look at the graph. Between 8 and 18 seconds, what do we know about that velocity? Seriously, what do we know about the velocity between 8 and 18 seconds? Yeah, it's constant. If it's a constant velocity, then what do we know the acceleration is? 0, right? 0. You could say delta V over delta T. Delta V is 0. 0 divided by 10 seconds is 0. Or you could just say it's a constant velocity. We know its acceleration is 0. Displacement. Here we got a triangle and a rectangle. Let's say the area of section 1 is 1/2 of base times height. 1/2 of the base would be 8. The height would be 5. Let's say area 2 is base times height because it's a rectangle. It's going to be from 8 to 18 is 10. The height is 5. So it's going to be 50 meters. And then what do we got to do with them? Add them up. Total displacement would be 70 meters. Hey, one more thing that I could have asked you there that I didn't. What's the average velocity over the entire thing? The average velocity of the entire graph. How would you do that? There's only one equation you can use for average velocity, right? V equals d over t. Now this is acceleration. How can I use d over t? Because I'm looking for the average velocity. The displacement we just found. It would be 70 meters divided by the time of 18 seconds, whatever that works out to be. All right? You guys comfortable with that? Comfortable enough to have a little quiz on it tomorrow? Good. All right, that's what we'll do then. We'll have a little quiz on it tomorrow. All right, we're going to spend just a couple of minutes talking about acceleration time graphs. Position time graphs, velocity time graphs, acceleration time graphs. The good news is, for these ones, we're not going to crunch any numbers. We're just going to take a look at a couple of shapes. What's the first one mean? If this was a position time graph, it would be constant velocity. Acceleration time graph, constant acceleration. An acceleration time graph, this would mean what's happening to the value of the acceleration? Here it's something. Here it's something bigger again. This is just increasing acceleration, right? This is like the graph for velocity time graph if it looked like this, increasing acceleration. What about the second one? We don't have the acceleration here isn't changing. So we're going to say it's a constant acceleration. If this was a velocity time graph, it would look like this. And finally, this would be a decreasing acceleration. We're not saying it's going backwards. We're not saying it's slowing down. It's not slowing down. Its acceleration is still positive. It's speeding up. But the rate at which it speeds up is decreasing. It's like putting your foot on the gas pedal and then easing off. You still speed up, but not as quickly as you were before. Look, that's all we got to know. For acceleration time graphs, that's all we got to be able to do. This will not be on your quiz tomorrow. And because it's such a small thing, we're not going to have a quiz on it. But be prepared on your unit test to see any of the 5 shapes that I gave you for position time graphs, velocity time graphs, or any of the 3 shapes that I gave you for acceleration time graphs. Be able to distinguish between them all. Between the, 13, I guess, different shapes of graphs.